Assalamu alaikum. Welcome to lecture 16 of natural language processing. So I hope all of you are doing well. Uh, so today we will continue and wrap up our discussion on fixed uh, embeddings, or in other words, learning embeddings from data. And we were talking about Word2Vec last time. So we'll discuss Word2Vec and discuss very briefly some properties of embeddings in general. And then we will move on to sequence modeling, starting with some applications like POS tagging, part of speech tagging, and named entity recognition. And then, of course, after that, which will probably not be in this class, but in the following classes, we will be discussing sequence modeling approaches, starting with the probabilistic approach to sequence modeling and then moving on to neural networks. So, so we are into the second half of the semester, so time is going to fly now fairly quickly. Uh, so I have posted details of your project. So the project primarily involves re-implementing some recent research work. And for that, you will have to choose a paper. And of course, that is part of your learning as well. You need to search for the paper and look at the details and see if that is implementable or not. And so you will need to decide on some papers by next week. Of course, during this week, you need to decide on the groups. You can have up to 3 people within a project. So in the previous years, I used to have a slightly more extensive project. But this year, I have kind of cut it down a little bit and just focused on implementing some recent work, uh, and kind of not spend time on literature review and developing a methodology or stuff like that. So the whole idea is that you are exposed to literature, and then you're also exposed to some of the topics that are discussed in recent works. And then you have some idea of implementing those models, uh, implementing and evaluating those models. So that would be your project. So please start working on the project as soon as possible. Of course, you will have assignments as well in parallel. So you need to uh, manage your time appropriately. So any questions? So in the last lecture, we had started talking about Word2Vec, which is a technique for learning representations for words or any other linguistic unit. And this approach uh, is based on classification, and so it's based on prediction. But the idea is that we are not focused on the prediction model, we are focused on what the model has learned as part of the prediction, and the weights that are learned during the learning process are actually what we are interested in. So those weights would actually be the embeddings or the vector for the word that we are interested in. So I had started discussing this last time. The original Word2Vec approach proposed two techniques. One was called the skipgram approach, and other was called the continuous bag of words approach. In the skipgram approach, the idea was to predict the context word given an anchor or target word. and the context of any given anchor word is defined by a window around it. So if you talk about a specific word, then the context word would be some number of words after it plus and some number of words before it. So usually this would be plus, let's say, C minus C, where C is the size or the number of words before and after that particular target word or anchor word. So basically, essentially, we will be building a multi-class classification problem or building a multi-classification model and specifically a neural network model to predict the context word given the input word. And how many context words would we possibly have that would be equal to the number of words in our data set or the vocabulary size. And the input words at the start would be represented as one hot encoding. So if you have a vocabulary size of M, meaning that you have M distinct words in the corpus, so you will have a vector of size M, and for each word you will have one possible one there and all the others would be zero. So for example, if you want to represent the word science, so science, let's say, is represented by the 350th position. So you will have a 1 at the 350th position of the vector and zeros elsewhere. So this is called the one hot encoding. So the whole idea of one hot encoding is that you can represent a large number of items in a fixed vector size. So that's the idea. Of course, this is a very simple representation technique, identical to representing words by their IDs. Now, essentially, the ID is the position of the word in the vector. So as I said, this is supervised learning, but the labels for the learning, remember in supervised learning, you have input and you also have the class label. The input, of course, as I said, is the anchor word. The class label is the context word. And we can get these labels directly from running text. So we don't need humans to label our data set. So in other words, this is also sometimes called self-supervision. So labels are already available in the data set of interest, which is just text. So let's say I have a simple text, Lahore University of Management Sciences. So these are words in basically a running text. And let's say we define a context of +1 words and -1 words, meaning that given any anchor word, we will consider the context to be one word before it and one word after it. So if this is our running text, our input, our training data set would be something like this. So input, let's say if we take the first word Lahore as the anchor word, then the next word, which is +1, would be the context word, which would be the output of the classifier, which is university. Of course, there is no word before Lahore, so there is no context before Lahore. So if you take the next word as the anchor, then of course Lahore is an anchor, a context word, and also off is a context word, which is the next word after university. And then similarly, we continue off, which is the next target word or anchor word, and then we have university, which is the preceding word, and then of course management. And then so on. So after that, we'll have basically management as the anchor word and so on. So in this way, you are generating the training data set. So now let's look at the neural network. So we have a two-layer network. So two-layer feed-forward network. So fully connected feed-forward network. So input layer is of size m. So why is it of size m? Because we are representing each word with a vector of length m. So we have m units in the input layer or in the input, which is also sometimes called a zeroth layer. Okay? So we have m inputs corresponding to the representation for words. So then we have one hidden layer, which is the first layer. And let's say its size is h, meaning that there are h units in the hidden layer, and this is of course kept less than m, and we will see why this is taken as such. And the output layer, which is the second layer, is also of size m. Why is it of size m? Because we are doing a m class classification problem. We want to predict the context word, and how many possible words do we have in the context? All the words in the vocabulary, and we have, of course, m words in the vocabulary. Okay, so I hope you understand this. So now let's define the weight matrices from the input to the output. So we had done this earlier as well when we were discussing feed-forward networks, but now let's look at this one in particular. So let's say W1 is a weight matrix from the input to the hidden layer, from the zero to the first layer. So what would be the size of W1? So usually it will be H by M. So hidden layer is H, and then M is of course the input layer. Of course, you will have a bias term as well. So sometimes we include this M in the bias, sometimes we don't. Actually, I will add it here, M plus 1. So this is my parameters from the input to the hidden layer. And then W2. In W2, we have M as the number of units in the output layer by, and the hidden layer is basically H, and you have a bias term, of course, 1. So these are the sizes of the two matrices. All right. So now, of course, the hidden layer activation function could be tangent hyperbolic, or it could also be rectified linear unit. We had talked about this before as well, rectified linear unit. And what about the output layer? So output layer, since this is multi-class classification, this is softmax. Of course, we will discuss how Word2Vec modifies this later on, because softmax becomes inefficient because we have so many classes, M classes, and M usually for most practical cases will easily go into tens and hundreds of thousands. So any questions so far? So this is the setup for the prediction model for predicting the context word given a anchor or target word. So as in all of neural networks, we start with randomly assigning weights to the weight matrices or the parameters. So usually W1, W2 would have values in the range, small values. Generally in practice, we keep it between 0.5 plus and minus 0.5. So of course, randomly. Okay? So randomly assign values initially. Of course, this is initial. And then, of course, you have the training data set where you have the input represented as one hot encoding. You have the output, which is one node in the output layer of course, corresponding to its position in the vector. And you have, of course, a M-class classification problem. You have initiated or initialized the weight matrix. Then, of course, you apply the stochastic gradient descent optimization. So which will basically solve the problem. We discussed briefly this. Basically, we will be minimizing the multi-class cross entropy loss function at the output, which is appropriate for multi-class classification. So once you minimize this, once your network has stabilized, you will have the final matrices. All right. I mentioned star to ensure to distinguish it from the previous one. Star basically means these are the optimal stabilized values of the parameters of the network. So now we have learned a model that given a anchor word would give you a distribution over the context word. So let's say if I give an input word, let's say I say input word is, so let's say intelligent. So you'll have, for this word, input word, the network give you a distribution over the output word. So the context word given intelligent. And this would be a distribution. So you will have a probability for, let's say, probability of D given intelligent. So let's say this is 0.001, let's say. So you'll also have probability of, let's say, A given intelligent. Let's say this is 0.05, and let's say, and so on. So probability of, let's say, computer given intelligent. So let's say 0.005, and so on. So you have the complete distribution. And of course, if you want to do a classification problem, what would be the best label? The word that has the highest probability. Okay? So that is most likely to occur in the context of the word intelligent. Most likely. Of course, as I said, it's a distribution. You might have other words that have close probabilities to that, probabilities that are close to that particular word. All right, so we have learned this model, but of course, this is not our goal. Our goal are actually information from the weight matrices. So let's go back to the weight matrices. So let's say we talk about W1. So of course, this is star. I will not probably write star just to notation simplicity. So W1, as I said, was what? Size was what? Size was H into M. So I'm now omitting the first column, not writing +1. Of course, you can write it if you want to. Okay. So if you talk about a particular word, let's say if I talk about the word Lahore. So Lahore, as I said, was 350th position in the one hot encoding. So if I multiply Lahore, so W1 into, let's say I have the vector X Lahore, which has a 1 at the 350th position. Okay. So if I multiply this W1 with X, so what would happen? So X has a 1 in the 350th position. If you multiply this matrix, so the 350th column of this matrix would be outputted, right? 350th column, because बाकी सारे 0 हैं, सिर्फ 350th जो कॉलम है वो एज इट इज आउटपुट हो जाएगा, 1 वेक्टर आएगा आपके पास. So this word, this vector actually thus is a representation for this word Lahore. So what is the size of that column? Size is h. ठीक है? What was h? The number of hidden layers. And of course, this matrix corresponds to the matrix from the input to the hidden layer. So now we have, so the 350th column of W1 is the embedding for Lahore. And what is its size? So let's say E is the vector. So इसका size क्या होगा? H. And this vector, of course, would be dense, meaning that you will find very few values that are zero. Almost all of the values would be non-zero. And uh, it captures the information of, so basically information for Lahore based on the context in which Lahore appears with respect to other words in our running text. And it does this implicitly. So there is no explicit definition for what is the first position of this vector, what does the first position of this vector represent, what does the second represent, what does the 300 represent, and so on. So implicitly, it captures the relevant information from the running text based on the problem that we have formulated, and it has basically given us a dense vector of size h. So usually h in practice is an integer, of course, between, let's say, 50 to about 1000. So in other words, this is the embedding size. So similarly, like the embedding for Lahore, you will have embedding for other words as well. For example, university. So let's say if the university is, let's say, the 1000th position. So then embedding would be the 1000 column of W1. And similarly for all other words. So any questions so far? So instead of having a representation which is just the ID captured as a one-hot encoding of length m, m of course is, as I said, typically very large, tens of thousands, hundreds of thousands. We now have a dense embedding for each word, which is of size h. And h, of course, as I said, is user-defined, and it varies, or it can be varied from 50 to 1000. Usually in practice around 300, 256, 128, these are the common number of sizes of the vectors, 300, 600, 500, and so on. Okay, actually in this representation, in this model, we also had the other weight matrix W2. So W2 had a size of what? If you omitted the bias column, it had a size of m times h. So again, you have the h there, and the m, of course, correspond to again the vocabulary. So for example, if you talk about the 1000 position, which is for university, so for the 1000 position, the 1000 1000 row of this matrix would also be a embedding for the word university. So let's say if you're talking about university, which is 1000 position, then the 1000th row of W2 is also an embedding for university. So actually, if you think about it, this model has given you two embeddings for each word, one from the matrix W1 and the other from the matrix W2. Okay? So you can use both of those embeddings separately. Sometimes you can concatenate them. So what are the options that we have? So we can, for example, concatenate the two embeddings, which means that the embedding that we get, final embedding we get for any particular word would be of size 2 into h. Other options are just choose one. So usually from W1, of course, there isn't any strong theoretical reason for doing that, but kind of convention, you can say, in practice. Or then you can say you can take the mean of the two embeddings. Okay. And of course, here again, in the latter two case, you have embedding size of h, not 2h. So is that clear? So we had used a feed-forward neural network, a two-layer feed-forward neural network, to train the prediction problem of predicting the context word given an anchor word. And for this, we used running text. From the running text, we were able to get the labels for each word. We trained the model as by solving the multi-class classification problem. And uh, once the once the model has been learned, we were able to get the embeddings from the two weight matrices W1 and W2. So now a couple of other things. So far we have discussed this problem as a multi-class classification problem. And we had the softmax at the output. So if you remember, the softmax is a coupled to compute the softmax, you will have to compute the output of all the M nodes. Because if you remember, the softmax is normalized by the sum of the outputs of all the other words. So you'll need to compute the output of all the other words. So it turns out that if you have M as an output, M is, as I said, very large. So softmax computation becomes quite expensive. So the people who propose this Word2Vec, they propose a simplification technique as well. They said they converted this problem to multiple binary classification problems. So if you have a binary classification problem, then you have the sigmoid, of course, which is what the probability that a particular word is a context word or not. Okay? And of course, using the sigmoid would decouple your particular unit's output from the output of the other units. But to do this, you will also then need, so for example, now what is the question here? So let's say आपके पास anchor word Lahore है और output word let's say university है, context word university है. So we are building a classifier for just this problem, where input is Lahore and output is university. And of course, this is binary classification. Either it is university or it is not university. Okay? Similarly, for all the other words. So let's say you have another word like of university. Okay? And let's say the university and so on. So we have a binary classification problem. But as you know, for a binary classification problem, you also need to have other words that are not. So you need to have positive examples. You need to also have negative examples. So you also need to have words like the, not university. And let's say other word like live, not university. So negative samples bhi aapko chahiye if you want to solve this as a binary classification problem. So what they do is, for any given input, let's say Lahore, and output pair, university. So let's say university is a context word for Lahore. And let's say लाहौर का और कॉन्टेक्स्ट वर्ड्स भी हैं, लेट्स से लाहौर का यूनिवर्सिटी ऑफ कह दें, ठीक है. So these are context words, but then also you also need non-context words for Lahore. So Lahore, let's say intelligent, for example, is not a context word. So negative words भी चाहिए आपको. अब negative words usually, since the context window is very small, the number of possible negative words may be huge. So what they do is they just randomly sample some negative words, some k number of negative words for each anchor word. So as such, you have, you basically then develop a data set through negative sampling. So let's say I'm talking about Lahore. So Lahore ka ek university hai. This is a positive word. And then of course Lahore ke liye, let's say di hai. This is also a positive word. And then Lahore ke saath a number of negative words, up to let's say k negative words that do not appear in the context of Lahore, but these are randomly sampled. Okay? And usually K would be, let's say, the thousand, maybe, not hundreds of thousands. Remember, vocabulary size is usually hundreds of thousands. So, so now what happens? So if we talk about the neural network, so let me see if I draw this. So if we talk about the output layer, so we have several nodes, right? Previously, we had to compute all of them together because we were doing the softmax. Now, we will compute any single layer separately. So it has its inputs coming in using the softmax as the sigmoid function. So each node is computed independently. So we select one node, you can even say randomly. And then for that node, we have its target. Let's say this node is for the output university. Okay? So for the word university, we basically take all the inputs, update these weights, but to update these weights, you also need the negative example. So those negative examples will be randomly sampled from the set of possible units, and those would also be updated. So in other words, you are selecting one unit and you're updating that using the positive examples. And then for the remaining units, you're randomly selecting some negative examples and you're also updating them. And of course, each update is independent of the other using the sigmoid, because sigmoid just uses that node and its corresponding weights. Of course, applying using the backpropagation and stochastic gradient descent. So instead of computing all nodes every time, we compute one node independently and some other nodes independently. Of course, those other nodes are randomly chosen. And this is done, of course, repeatedly until the network converges. So this approach is basically to fasten or speed up Word2Vec learning, and it's called negative sampling. So we are converting a multi-class classification problem to multiple binary classification problems. And for that, we also need some negative examples. Those negative examples are randomly selected for each node. Okay? So this as a whole approach is just called skipgram with negative sampling. So in the original paper, by the way, this paper was Word2Vec paper was published in 2013. So since 2013, lots of extensions and variations have been proposed. And since 2013, NLP has been transformed significantly because of this discovery. Because embeddings are much richer representations for words and other linguistic units, and they help improve the performance of downstream tasks. So you can think of any downstream tasks like topic classification, sentiment classification. Later on, we'll talk about language modeling, as well as POS tagging and named entity recognition. All of those improve because of these embeddings. Okay, in the original paper, they also proposed another approach, which they call the continuous bag of words. Or simply CBOW. Okay. So this is actually very similar. So previously we had done input was anchor, output was context word. Here input is context word, output is the anchor word or target word. So we have flipped the roles. So given a context word, we will predict the word in the middle, the anchor word. So while in skipgram, given the middle word or the anchor word, we predict the words in the context. So this was called continuous bag of words, and you have the similar model and similar embeddings. Of course, the embeddings was slightly different, and those differences because of randomness as well. But in practice nowadays, people more or less use the skipgram approach. But in the original paper, they also introduced the continuous bag of words approach, which was the reverse of that. Given the in context word, predict the target word. All right. So, so these are basically called static embeddings, as opposed to dynamic embeddings, which we'll discuss later on. Why they are called static embeddings? That once, so in other words, for each word you have a fixed embedding, and that embedding is learned from some corpus that you use to train your model. Once the embedding has been learned from that corpus, it remains the same for whatever application you are going to use it for next. So it is not context dependent, it is fixed from the context that is learned from the corpus. So these are called static embeddings. So what are embeddings? As I said, embeddings can be represented as points in high dimensional space. So let's say we have 300 size embedding. So you can represent each word as a point in a 300-dimensional space. And multiple words, of course, would then be multiple points in that space. And since of course embeddings capture a lot of information about those words, we can you can study words by their, you can say, closeness in this 300-dimensional space. And one way of quantifying the similarity, of course, is, as I said before, is cosine. So you take the cosine between the two vectors. So let's say आपके पास एक लाहौर की embedding है E let's say 1 है और एक यूनिवर्सिटी की embedding है E2. You take the cosine of E1, E2, which of course is the inner product of E1 and E2 divided by the lengths of the vectors E1 and E2. Okay, so you can write this as E1, E2. So this is the cosine of the angle between these two vectors in the 300-dimensional feature space. If this cosine is small, you can say that these two vectors are similar. So since 2013, people have spent a lot of time trying to study words in this space. And many interesting things have been discovered. So some of it is interesting, some of it is sometimes spurious in the sense that, of course, it might be found to be interesting for a particular example. It may not hold in general. So, but still, as I said, there's a lot of positive information that you can get from embeddings. And this part, actually, I don't want to go into too much detail. You can read it up because most of this is kind of reading. So you can read this relevant sections in chapter 7, I think section 7.7 and onwards. So, okay. So one thing is, of course, if you want to study lots of words, you can plot them in 300D space. Of course, 300D space, you cannot visualize. So people often then project this 300D space into, let's say, 2 or 3D. So basically, maybe using PCA or SVD or some other dimensionality reduction technique, reduce it to 2 or 3D, and then study those points. So if 2 points are, or if you have a bunch of points that are close together, then you can say that those points are, or those words which those points represent are related. Remember, we made the distinction between similarity and relatedness. Similarity is essentially same sense or similar sense, while relatedness may be related in some semantic field way, and that semantic field may even be antonyms, or they might be concepts like a concept of, let's say, university, a concept of hospital, a concept of computer programming, and so on. So you can study words by plotting them in 2 or 3D space. And you can get insights into how those words are related in the given corpus that you had used to build those embeddings. So that's one thing. Another thing is people have found out that you can do interesting, or you can determine interesting analogies using embeddings. So analogies, and of course, this is an area which was found to be very interesting earlier on, but later on people found that this was not true in general, and the results that were shown were generally few of the kind. In general, they do not hold. And some of the results were something like this. Let's say if you took the, for example, if you take the embedding of queen, for example, and then subtract the embedding of, let's say, man, subtract the example of woman, you will get an embedding that is very close to king. So of course, a queen is a female, and if you subtract from the embedding of queen, the embedding of woman or male, sorry, or female, you will get an embedding that is close to that of king. So इस तरह की analogies people लोगों ने काफी discover किए हैं, but it is okay, interesting, but you cannot generalize it to every kind of analogy. So it's kind of difficult to generalize it. So इस तरह की और चीजें भी आप कर सकते हैं. For example, so जैसे husband हो गया, husband. Of course, I'm giving examples for male and female, but ये और जगहों पे भी चल जाता है. Husband minus let's say male करें तो ये wife आ जाएगा, and so on. You can have examples from others as well. For example, doctor plus let's say doctor plus hospital. I don't know, इस तरह की analogy. मतलब there are some people have come up with interesting analogies, and you can look up some of those examples in the book as well, and there are papers on this as well. So what does this show? Embeddings capture lots of information, and simple algebraic operations could give us additional insights. So these are algebraic operations. So you take a subtraction, you do a addition, and so on. They might give you some other insights. Of course, these are vector operations, vector addition, vector subtractions, and so on. So that's another thing, analogies. The third thing that I want to talk about is people have used embeddings to study the evolving use of words over time. So as you know, in the 19th century, English was markedly different. So of course, if you talk about the Shakespearean English, it uses words that are spelled differently, that are pronounced differently, and it might even use some grammatical structures that are now less commonly used in English today. So people have kind of studied these variations over time by building embeddings for, let's say, all the writing that were done in the 19th century, all the writing that were done in the 20th century, all the writing in the 21st century, build the embeddings and compare those embeddings. So people have done this analysis, and they have found very interesting results. So historical, cultural. So actually this is over time, but then of course you can say also have study word usages over space. So space would mean, for example, culture, national, religious, etc. So for example, the way people use English in Pakistan, there might be differences to the way people use English in the US, for example. So several things, for example, just to give you a very quick example, for example, in the US, the shopping cart that we use is often called a cart, while in Pakistan and maybe even British in England, they usually call it a shopping trolley. So differences like these could also be discovered through learning embeddings over corpus that are written in the UK and over corpus that are written from the US. And you will find that trolley and cart would be almost identical. The vectors for trolley and carts would be almost identical from the two corpuses. So that's about historical, you can say, analysis of words. You can also say his spatial or geospatial analysis of usage of words, cultural usage of words, religious usage of words. So linguists and other people have studied this quite extensively since 2013. And finally, there's also an issue of bias. And so remember, all of these embeddings are learned from writings that are written by humans, of course. So whatever bias that exists in those writings would also be captured in the embeddings or will also be brought to the embeddings. And if you use those embeddings in applications, those biases may be transferred or sometimes even magnified to those applications. So, for example, biases, gender bias, for example. So, for example, you will find that a doctor, the vector for a doctor would be more related to, let's say, a man than to a woman. Why? Because in writings, you will find whenever there's, or most of the cases when we talk about a doctor, it is usually a man. Similarly, on the flip side, a nurse would be related to a woman, more to a woman than to a man. Because whenever nurse, or most of the time nurse is mentioned, usually it's a lady or a woman or a female. So such biases would also be, you can say, embedded in their embeddings. Right? And then, of course, you can have various other kinds of biases as well. For example, racial biases also persist. People have figured out that, uh, for example, whenever you talk about a Black African American, for example, so African American, African American would be more closely related to crime than a non-African American. Okay? So again, these are biases that we will not like to continue in most downstream applications, and we would like to mitigate that. So in general, biases do creep up into embeddings because they are learned from writing that are biased or written in a certain way. But in downstream application, we would like to mitigate that. So recently, there is a lot of work on, first of all, of course, bias detection and quantification. And then secondly, once you are able to properly quantify the bias in your embeddings, then the next step is bias mitigation. So this is an active area of research, an area in which we have worked as well, not very extensively, but we have worked. And so these are a couple of areas that are still active in research. Of course, you can have very simple techniques as well. So for example, let me say, so for example, let's say, uh, so you have the vector for, let's say, a doctor. So this is the point vector for a doctor. Okay. So doctor would be, So let's say ये vector doctor ये point doctor का ये vector मैं draw कर रहा हूँ, ठीक है, something like that. So let's say this vector of doctor is very close to the vector of a male. So this is vector of male, while nurse का vector इधर है, ठीक है, very far away from that of a male. Of course, this is similar to a female. Let's say female का vector इधर है, ठीक है. So what people have done is male female के जो vectors का जो common vector है वो बना लिया. So for example male का ये था और female का ये था, इनका एक common vector बीच में बना लिया. And then they projected the vector for doctor and nurse to this vector. Now, of course, doctor and nurse would then become unbiased. Of course, this is a simple way of unbiasing vectors. So आपके पास जो जेंडर न्यूट्रल वेक्टर लेट्स से ये है, ही शी दोनों यही है, मेल फीमेल भी यही है, व्हाटएवर प्रोनाउंस दैट आर यूज्ड फॉर मेल एंड फीमेल. अब आपके पास लेट्स से डॉक्टर ये था, तो इसको हमने इधर प्रोजेक्ट कर दिया, ये डॉक्टर इधर बन गया, और जो आपके पास नर्स इधर था उसको भी इस पे प्रोजेक्ट कर दिया. बोथ nurse and doctor would now become gender neutral. So, of course, this was an earlier technique that was used to mitigate or remove bias. All right. So this was, I think, probably the end of chapter 7. So please read this chapter. Most of this stuff we have now covered. Okay, one thing, as I said, these are static embeddings. So pre-trained models embeddings are available on the web. So for example, Word2Vec embeddings are available in different sizes that have been trained on large amounts of data, on the entire Wikipedia data, on the entire website, and so on. So all of those embeddings are available. You can download them and use them in your application. And they are available in different sizes. So 300 का भी मिल जाएगा, 500 का मिल जाएगा, 1000 का भी मिल जाएगा. So this is a huge resource for NLP application developers. So pre-trained embeddings are available. They are also available in different languages also. Urdu की भी एक available है. हमने खुद ही भी बनाई हुई, but net पे भी available है. तो and of course all other languages की भी available है. Okay, so we talked about Word2Vec. Static embeddings में और भी techniques हैं. So one is called global vector, GLO, GLOB. So global vector is based on co-occurrences. Remember we talked about the word-word co-occurrence matrix last time. So global vector is a dense approach, not a sparse approach, but it's primarily based on co-occurrences of words in context. It's not based on prediction as the Word2Vec, but it also yields good dense representations. So GLOB is a popular technique as well. Then there is another technique from Facebook called fast text. And fast text is also static. One of the advantages of fast text is also character based. So this kind of solves the out of vocabulary problem. So let's say if you have a weird word that was not available in the training data set, obviously it would not have an embedding. But fast text is character based. So whatever those sequence of characters is C, E, T, A, R, let's say. So let's say you have a word like this, it would be able to give you embedding based on the characters. Okay. So fast text is also static embedding, but it's character based as well as word based. GLOB, of course, is primarily word based. And then Word2Vec is also primarily word based. Of course, Word2Vec, GLOB, you can also train it using characters or subwords, as we talked about earlier, subwords. You can train it yourself. But most pre-trained models for GLOB, Word2Vec, as well as fast text are based on words, and they are available on the web. All right. Okay, now let's move on to sequence modeling and applications of sequence classification. So as we have been looking at text since the start of this course. So text, as I said, is a sequence of characters. So essentially, most of the applications of text of NLP would benefit from sequence modeling the how characters as well as words are used in sequence. Okay? So, so two popular applications of sequence modeling and specifically sequence classification is what is known as part of tagging, and the other is what is known as named entity recognition. So this is often abbreviated as NER, and this is often abbreviated as POS. Okay? So these are two common tasks of NLP that are sequence classification tasks. So let's introduce this task, and then we'll discuss sequence modeling in general, starting with probabilistic sequence modeling and then moving on to neural networks. So what is POS tagging? So part of speech. So we talked about part of speech when we discussed linguistic briefly at the start of this semester. So, so part of speech is basically a grammatical function for a word. Uh, so, and we have various parts of speech for different languages. So, for example, in the English language, you have, for example, noun, you have verb, you can have adjective, you can have adverb, you can have preposition, you can have conjunction, and so on. So these are word classes or linguistic classes, or you can say morphological classes of words. Okay? And words within each class have a specific grammatical function. And of course, they have some specific semantics as well. But the grammatical function is important because those properties define how correct language is written. Syntax, what is a correct syntax for a particular language. So of course, nouns, if you go into linguistics, you will have further subclassification as well. So nouns could be proper nouns and common nouns and so on. So names of things would be nouns, names of people would be nouns, names of locations would be nouns, and so on. Okay? So, and then of course, verbs are action words essentially. So they describe some form of action. And then of course, adjectives usually qualify nouns, adverbs usually qualify both nouns and verbs. Prepositions, of course, kind of define the relationship between two nouns in sentence. For example, prepositions would be like under, in, over, words like all of these are prepositions. And of course, I think there is so you can also have what do you call as determiners or no, for example, articles. So A, D, so these words could also be parts of speech. So what is the task or part of speech tagging? So these are just a quick introduction of POS. We will discuss this starting next class as well. We are running out of time. So, so what is the task of POS tagging? So, so I live in Lahore. Let's say this is a sentence, running text. The task of POS tagging is, given any running text, we would like to identify the proper POS of each word in that text as it is used in that particular text. Of course, a given word may have different POS. Okay? And as we said previously, a word may have multiple senses. And each sense may fall in a different category or in a different POS. So in POS tagging, we would like to identify the correct POS for a given word in context. So of course, in this case, I would be what? I basically is a pronoun actually. ठीक है, so pronoun मैंने ऊपर नहीं लिखा. Pronoun भी एक POS है. So let's say this is a pronoun, PRO, and then live. Here in this case, live is a verb, not an adjective. ठीक है. In here, of course, is a preposition. ठीक है. And Lahore here, of course, is a noun. ठीक है. So given any sequence of words, we would like our model to label the words with the appropriate POS tag. So this task is of course called POS tagging. ठीक है? So for example, if you have another word, he watched the match live. In this case, of course, he is a pronoun, P-R-O, let's say, P-R-O, let me just write really quickly. Watched would, of course, be a verb. The watch the match. The would be a determiner, for example, and or article, and the match here is of course is a noun, and here live is now an adjective. It's not a verb. So a particular sequence of words, a sequence of characters, or a given word may be from different word classes or morphological classes or POS. Okay. All right. So what are the applications of POS tagging? So POS tagging has numerous applications or advantages. So for example, stemming lemmatization would benefit quite a bit from POS tagging. If you already knew the POS tag, you will be able to better stem or do lemmatization for that particular word. So pre-processing would be helped if you are able to do POS tagging. What else? So for example, if you are doing sentiment analysis, so POS tagging would help. You will be able to identify, for example, nouns, which are the words about which opinions are expressed. Then adjectives, for example, adjectives would be generally the polarity words that are expressing the opinion about those nouns. You can also keep, for example, adverbs. They kind of amplify, de-amplify the adjectives and so on. So again, POS tagging would help here as well. POS tagging also helps in parsing. Parsing, of course, is given running text. We would like to divide that text into its linguistic units. For example, phrases, clauses, conjunctions, and so on. And parsing, of course, is a a subtopic in NLP, which we won't be discussing in this course. Uh, so parsing essentially means that trying to understand the different components of a sentence. So peer tagging would help in that as well. And and of course, in many other application, information extraction in general. So information extraction. So for example, if you want to extract names from running text, so you will have to identify nouns. For example, if you want to extract locations from running text, you will have to identify nouns and so on. And even it's useful in machine translation, for example. So if you're translating from, let's say, Urdu to English or English to French, for example, so a noun, for example, would not be translated. Noun would remain the same in a different language. And of course, if there's a verb in one language, you would like to have a similar verb in the other language. So actually, in general, so these are just some examples. Actually, POS tagging explicitly or implicitly plays a significant role in almost all NLP applications. So if we are able to identify POS tags, then for many applications, our performance would improve. Okay? So I think I'll stop here. And next class, we will discuss briefly the NER problem, and then we move into the probabilistic sequence modeling approach. The probabilistic sequence modeling approach has now been removed from the main body of your primary textbook. It's now an appendix. But I still feel that it's important that we discuss this because when you study probabilistically something, you get a deeper understanding. On the other hand, if you study using neural networks, it just appears like a black box. So that's why we will discuss the probabilistic approach and then move on to the neural network. Any questions? So today is Tuesday. So we'll have a quiz, inshallah, on Thursday. So, and this quiz would cover all content from since the midterm. So we have 3 lectures. Any questions?